Hi everyone, I'm John Poprosky and welcome to my webinar on how to convert S-parameters to causal S-parameters usable in any channel simulator. Please type any questions into chat as I proceed with this webinar. I'll have a questions and answer session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuits and serializer-deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or own. Today, the SerDes channel simulation technology has matured so that it's available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations or from hardware measurements. This webinar is to let you know about the process I've used for many years to generate causal S-parameters usable in any channel simulator, and it's available to you for free. What is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools prevent your chances of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, JavaScript, and more. I learned that creating an IBIS-AMI model should be your last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit simulation or measurement data, and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com, with options to download and install local copies on your Windows or Linux machine. I am here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I've used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. It first gives you an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to convert ordinary S-parameters to causal S-parameters for use in any channel simulators. I discuss these topics. S-parameter background, including problems in time domain tools, and what are causal S-parameters, and an example with Keysight ADS using causal S-parameters. Finally, I show you how to use my free web-based generate causal S-parameter tool. Modeling SerDes systems in a channel simulator. Channel simulators are based on the IBIS Open Forum standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: the transmit IBIS-AMI model. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. There's the IBIS portion that provides a differential output to the channel. There's a transmit package, a channel, an RX package. These pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. There's the receive IBIS-AMI model. The IBIS portion has differential input from the channel. The AMI portion typically contains a receiver continuous time linear equalizer, a clock and data recovery unit, and a decision feedback equalizer. Modeling a SerDes system. A key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-headed impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. S-parameter background. S-parameters are used in modeling SerDes system channels, which have a typical structure shown in this figure. Each part of the total channel can be represented with S-parameters. Besides the channel itself, the total channel may include characteristics for a differential transmit package and a differential receive package. Optionally, the IBIS buffer and the receive IBIS buffer may also be defined with 4-port S-parameters and included in the total channel S-parameter representation. Let's talk about the differential SDD21 characteristic. The differential channel represents a hardware SerDes channel and is typically characterized by measuring its n-port S-parameters and is typically a 4-port. The 4-port differential input ports are typically port 1 for the plus side and port 3 for the minus side. The associated differential output ports are typically port 2 for the plus side and port 4 for the minus side. The differential transmission characteristic is related to the single-ended S-parameters as shown here. SDD21 is equal to 1/2 times the sum of S21 plus S43 minus S23 minus S41. Shown here is a typical SDD21 characteristic. The S-parameters go out to 40 gigahertz for a 25 gigabits bit rate. The Nyquist frequency is 12.5 gigahertz, which shows a 25 dB loss. At high speed, digital SerDes channel typically has a substantial high frequency attenuation at and above the Nyquist frequency and requires compensation using equalizers at the transmit and or receive side of the channel. S-parameters have issues when used with time domain tools. S-parameters, though measured on actual hardware, deviate from the constraints for physical realizability, such as passivity, reciprocity, and causality, or include noise in the measured S-parameters for various reasons. For physical realizability, the S-parameters should ideally be measured continuously from 0 Hz to infinity with no noise or distortion. For practical reasons, the S-parameters are band limited, are tabulated only at discrete frequencies, and are corrupted by measurement noise. Time domain simulators typically use sample rates that may be 10 times or more times larger than the S-parameter maximum frequency. To achieve a physically realizable transmission characteristics, the S-parameters must have corrections applied. These corrections must be achieved when converting S-parameters into an equivalent impulses in the time domain. All SerDes system channel simulators convert the frequency domain S-parameter characteristics into time domain impulse characteristics. While doing all such, simulators attempt to correct for all impairments in the S-parameters. However, some are less successful than others. In fact, all of the top 6 EDA channel simulation tools have problems in doing this, as has been observed by many, and especially reported by Romy Miter of Xilinx at the 2015 DesignCon conference, January 27 to 30, at the Santa Clara Convention Center in Santa Clara, California. The top 6 EDA channel simulators in the industry gave widely varying impulse modeling of S-parameters as well as widely varying channel BER performance for IBIS-AMI model simulations over 6 EDA platforms. SerDesDesign.com provides causal S-parameters. These have been in use for over 10 years for SerDes channels using S-parameter data. The SerDesDesign.com approach relies on correcting the S-parameter data in the frequency domain and on extrapolating the S-parameter data beyond the maximum S-parameter frequency, call that Fs-max, to half the sampling rate frequency, call that Fmax. For example, with Fs-max equal to 40 gigahertz, with a 30 system symbol rate of 25 gigabits per second using 32 samples per bit, then Fmax is equal to 400 gigahertz. The S-parameter corrections applied relies on these steps in the frequency domain. Adjust the S-parameter data for consistent time delay. Adjust the S-parameter data to meet requirements based on the Kramers-Kronig relations. Extend the S-parameter data to Fmax based on a scientific-based relationship between magnitude and phase. The Kramers-Kronig relations state that the real and imaginary parts of a causal response are related by the following Hilbert transforms, where U and V are real and imaginary parts of the spectrum, and P is the Cauchy principal value. This Kramers-Kronig expression, though looking complex, actually is simply applied in the frequency domain to make S-parameters causal. Extrapolating the S-parameters. The SerDes design approach for extending the S-parameters to Fmax derives the phase in the extrapolated region from the extrapolated magnitude response. As the above Kramers-Kronig relations show, the real and imaginary parts of a causal response are related. Similarly, it can also be shown that under certain conditions, the magnitude and phase of a causal response are related. The extrapolated S-parameter data also meets the requirements of the Kramers-Kronig relations. The causal S-parameters have an entire set of S-parameters derived for endpoints from 0 Hz to Fmax, where n is a power of 2 plus 1. Once these S-parameter corrections are achieved in the frequency domain, the inverse f of t of this data using a 2 times n point results in causal time domain responses. SerDesDesign.com causal S-parameters have been in use for over 10 years for use in converting S-parameter data to its equivalent causal representation in the time domain. The approach preserves the fidelity of the S-parameters up to their highest frequency while eliminating the high-frequency aliasing at higher frequencies with no added delay. Here's a causal S-parameter example. This example discussed here is specific, but the concept applies to any S-parameter file. For this example, consider the S for P data defined earlier with the SDD characteristic that was displayed. The S-parameters have a maximum frequency of 40 gigahertz and are intended for use with a maximum symbol rate of 25 gigabaud. Here's the display of the transmission characteristics for the S21, S41, S43, S41, S31, and S43 characteristics. The causal S-parameters can be displayed. Using the free Generate Causal S-Parameters tool, the original S-parameter file can be converted to causal S-parameters from 0 Hz to 400 gigahertz, where 400 gigahertz is equal to the bit rate times the samples per bit divided by 2. And using the free Compare S-Parameters tool, the new S-parameters can be compared to the original S-parameters. SA, red, is for the original S-parameters and go up to 40 gigahertz. SB, in blue, is for the causal S-parameters and go to 400 gigahertz. Log frequency scale is used. The causal S-parameters match the original S-parameters, and the extended causal S-parameters have no high-frequency aliasing. The causal impulse response. The causal S-parameters can be converted to causal impulse responses by using an inverse f of t with 2 to the n points, where n plus 1 is the number of frequency points in the causal S-parameters such that n is a power of 2. Here are the causal impulse responses for S21, S23, and SDD21. The original S-parameters have an inherent time delay of 18 nanoseconds. The resultant causal impulse responses also have a delay of 18 nanoseconds with zero response before that time delay. And they introduce no distortion and no additional delay. Here's a SerDes setup in the Keysight ADS channel simulator. The example original S-parameters and the causal S-parameters were used in the ADS tool. The channel has 25 dB loss at Nyquist, which is 12.5 gigahertz. Thanks to Silicon Creations LLC for the use of their ADS copy. The source is NRZ with 25 gigabits per second using 32 samples per bit. Bit-by-bit mode is used with 10,000 analysis bits using a PRBS register length of 13. The TX-AMI is an FFE equalizer with 3 precursors and 3 postcursors. The RX-AMI portion is an ideal pass-through. The TX and RX IBIS buffers have 50 ohm source and load resistance per differential pin. The original S-parameters in ADS. Here is the ADS total channel impulse response in the frequency and time domains. Observe the high frequency aliasing beyond 40 gigahertz. The ADS simulation time is 13 seconds. The output I density is also shown. Notice the distortions in the I density plot due to the high frequency aliasing. Causal S-parameter channel in ADS. With the causal S-parameters, the ADS total channel impulse response in the frequency and time domains is shown here. Observe that there is no high frequency aliasing beyond 40 gigahertz. The ADS simulation time is 40 seconds. The output I density plot is also shown, and notice that there is no high frequency aliasing distortion there either. With no high frequency aliasing, the full fidelity of the TX output is visible. The cost of using the causal S-parameters in ADS for this example is the longer simulation time from 13 seconds to 40 seconds. With the causal S-parameters providing no high frequency aliasing, providing accurate characteristics that track the original S-parameters out to the original S-parameters original frequency, and provides an impulse response that has no high frequency aliasing and no additional distortion or time delay. Using the free tool. Use my free tool. You must register on my homepage, then go to my website at the web location listed here. Enter your S-parameter file and identify how many ports it has. The allowed number of ports are 1, 2, 3, 4, 8, and 12. The generated causal S-parameter file would have the same name, but with causal.snp appended to the name, where n is your number of ports. Set up the free tool. It is assumed that your intent is to use the causal S-parameters in a time domain tool, such as a channel simulator. Your original S-parameters should have a linear frequency sweep and not a log frequency sweep. Let your original S-parameter file have a max frequency of Fmax. You need to identify your maximum bit rate and the maximum samples per bit. The resultant sample rate would be bit rate times samples per bit, with the maximum causal S-parameter frequency set to sample rate over 2. The sample rate over 2 must be greater than 1.25 times the maximum frequency in your S-parameters. For data display purposes, you can identify the differential input and output pair of ports. Run the free tool. Select Run to generate the causal S-parameters, then select Download to download the resultant file. You can compare the causal S-parameters, data B, to your original S-parameters, data A, by selecting the Compare Run button. The causal S-parameters will provide a good match to your original S-parameters to their highest frequency, and then extend those S-parameters to the sample rate over 2. an equivalent alternative to the causal S-parameters. Though SerDesDesign.com has provided its free Generate Causal S-Parameters tool on the web for over 10 years, my personal preference is to include the SerDesDesign.com anti-aliasing algorithm within the IBIS-AMI model as presented in the Signal Integrity Journal, September 13, 2022. See this link for that paper. The custom IBIS-AMI models created and delivered by SerDesDesign.com has this AAA built into the AMI models. This is an equivalent or preferred approach to using the causal S-parameters presented above. The use of the AAA in the AMI models results in a faster channel simulation and relies on the AMI model to remove the channel impulse high-frequency aliasing along with no additional delay, while retaining the channel characteristics up to the original S-parameters maximum frequency. Summary. This webinar has presented the proven SerDesDesign.com technology for converting S-parameters into causal S-parameters, which has been used for the past 10 plus years. When used in Channel Simulator, the causal S-parameters eliminate any high-frequency aliasing that might occur beyond the original S-parameter maximum frequency, which is typically much lower than the channel simulation sample rate. The discussion of the Generate Causal S-Parameter tools included S-Parameter background, including problems in the time domain tools, what are causal S-Parameters, and an example with Keysight ADS channel simulator using causal S-Parameters. This webinar has been on a SerDesDesign.com free tool. SerDesDesign.com has provided free web-based tools for evaluating components and SerDes systems for the past 10 plus years. Use the Generate Causal S-Parameter tool at this website. Registration is required to use. Well, this completes the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. Thanks and goodbye for now.